To be the first video for fall of 2021, and we're going to do a statics review. I'm going to break this up into a number of videos. So this is for class 1. So right here, this is the problem we're going to do, but I do want to show you that I created these notes that I have posted in the notes section, and I really I think this is a good idea to use these. Print them out before class, and then you can write on them, and so I'll kind of demonstrate that as I go through. You could also download the PDFs and put them into like OneNote or that type of thing, and then write on top of those. It works pretty well. So let me use my document camera here, and so I have a big old pile. I reprinted out my entire thing. You can see there's quite a few. But let's go up to page 1 right here, or I guess page 2 of class 1. And so here we have it. Okay, so I refer to these as door handle problems because it always looked like a door handle to me when I was taking classes back a long time ago. And what we're gonna do this problem in several different classes over and over again. But basically, what we have here is a cantilevered beam. I have a little model of this thing I like to pass around in class. And the big idea in statics is that we want to figure out the reaction loads, right? The reaction forces that are inside this door handle. And you can see that we're pulling on it. So we have a force that's going that way that's going to tend to want to move this way, right there, right? We have a force that's going down that's going to try to turn the thing, right? So it's going downwards. So that's going to work to like twist this thing that way right there. And then we also have a force that's pulling this way, right? That's going to tend to make this break over. And when we're going to use this same problem here and look at stresses, fundamental stresses, and try to really cement our understanding of them. But first, we need to take a look at the reaction loads and find the reaction forces and moments that are taking place in this little part right here, which we're going to call the section of interest, right? So that's my reference to it. Now, we can do this in a couple different ways, if you recall from statics. But the king of all ways to do something in engineering is the free body diagram, right? That is the fundamental go-to tool that we have as engineers. And it's really important that we get good at them, because it doesn't matter how advanced of an engineer or what kind of field that you go into. If there's some type of physical part that you need to do some analysis on, the first thing you do is a free body diagram. Now, one of the difficulties of this problem versus some of the problems that you might have had in statics is that this is three-dimensional, right? So we and quite often in statics, what we will have done is to use cross products, vectors, and cross products to find what the moments are, right? And we'll talk about that in another video. But for right now, what we want to try to do instead of using cross products is just use our free body diagrams and do them in 2 dimensions and draw them out and figure out what the reaction moments are and reaction forces at each of these intersections in all 3 views. So we have this thing, and here's isometrically, we kind of like make it look like there. We want to be able to look at this and see what each of these views. Now I have them sketched out here, so it's a cheat. But this is something that you need to be able to do, to look at something and work your way through it. And it's not a skill that everybody it really has strongly. So if you don't feel comfortable with it, you're going to have to do a lot of different practice problems to grow that skill. Right? It's not something that's like, I think is like we're all born with. It's just something we kind of pick up, or we maybe to some degree or another. So don't just say, oh, I'm just not able to see things. It's just something you need to do a little bit more work on. All right. So we want to do the 3 views. Now it's a good practice here to come up with a coordinate axes and have that be the thing that helps us, guides us through. Right? So a lot of times we want X to go down this way. And a good little ruler can really help us out here. Right? So I have these little rulers right here. And, drawing these things really nice and getting them parallel, we can kind of see that this is the X direction. This is the y direction. I like to make it vertical y. And it's a right-hand coordinate system. So you take your right hand, that's x, that's y, and that's z. And you can see that x is pointing down to x, y is pointing upwards, and then your middle finger decides where z is going to go. So we have this as correctly as a right-hand coordinates thing. So we take a look at this thing and at this door handle, and quite often I'll go for the XY first. Here I guess must have been the XZ for the thing. But so the XY, we want to draw a view that looks like this right here, and I usually draw this like creepy little little thing with eyelashes. We're looking from this side, and we're seeing the X and the Y right in here. So we're seeing this long dimension right here. So this right here, this X dimension, that's going to be, well, we're going to do it like kind of to the center of the thing, right? That's going to be our 3 inches. And I'll use the inch symbol as part of that right there, right? And then looking also at the forces right here, this one is coming at us, right? So it'd be out of the paper, so we don't actually see it. But we do see this force, and we notice it's aligned in the X direction. So we label this right here as 1,500 pounds. And then we're also looking at this with this big creepy eye for this view, and we can see that this 800 is coming downwards. So put that on there, 800 pounds. Let's put a pin in this, right, for right now. Well, no, actually, let's follow through with it, right, as if this was the first thing that we were going to do. Now, taking a look here, this is the location. This is our section of interest that's right here. And the first thing I might want to do is put what the reaction forces are. Well, if I'm trying to pull it, and we're looking at it in this direction right here, if I have a force going this way, and I've broken it apart, now it's free, that's the free body diagram. So we're looking inside this part, and we want to see what kind of reaction forces are inside this. If there's a force coming this way, there must be a force coming that way. Right? Some of the forces in the X direction must equal to 0, so we will draw our reaction, and I like to use capital R's and an X right in there. And if this was a specific spot, I called it A and B. That's kind of not convenient. But if I had a specific location, if that location was just A, I might call that RAX, like with both subscripts down at the bottom. All right. So and then we could see that that's going to be. We could actually know this without doing the sum of the forces equals to 0 in the X direction, and we could just say we know that reaction is going to be 1,500 pounds to the left. Or we might going to call it negative 1,500 pounds if we're going to go positive, negative. But I think an arrow is usually better in our answer. We're also going to have, looking here, we're going to go in the Y direction. We can know that if we're pushing down that way, there must be a reaction going that way, right? It needs to balance out. So we could draw this in here, and I'll draw it on top of that little axis, and I'll label it RY. Right there. Okay, so we've got that labeled, but we're missing something. The sum of the moments must balance out. And that's usually the thing that we mess up the most and what we need to put the most amount of attention to. So we go ahead and draw that like right here, right? So inside this is this internal moment that's happening onto this thing. You could even think it's this part is imparting a load onto this section right here that's causing, this thing is placing a moment on here that will balance out the moment that's being caused by the loads. And if you look at this force, you can see it passes through this point, so it does not cause a moment. But this one does cause a moment. It's a clockwise moment. So this reaction moment right here that's inside has to be opposite from that. So we get a moment right here, M. And I like to give it a subscript. Well, this is a moment that is going about the z-axis, right? It's rotating about the z-axis. So I'm going to call that MZ. And if I was going to solve this, I would say the sum of the moments about the z-axis is equal to 0 right here. And It's a little confusing sometimes because I labeled this as MZ. This is the reaction moment at Z, whereas this is all of the moments about Z, right? So sometimes I think maybe what I ought to do is go MRZ, but I forget to do that a lot, right? So you might just see me call it MZ. But now this is a specific moment that's happening here. This is talking about all of the moments about Z. And we note that counterclockwise is our default positive, right? So we would write that MRZ. That's something that's happening on, and we're taking this moment about the z-axis, that location right here, and we see that this is clockwise, so it's negative, and it's 800, and the perpendicular distance of this force to here, the moment arm, that this right here is the moment arm, right? It's happening through here, and this length along here is the perpendicular to the force and causing it to rotate. So it's 3 equals 0. So we know that MRZ is equal to 2,400, and these are inch pounds, right? Well, that was pretty easy. That was not so bad. Now I'm going to do this other easy one. Let's do this guy right here. Now this is the YZ, and this looks like a creepy eye that's looking down that way right there. And we can see the Y and the Z, and the X is coming out at us. And if we go and we take a look at the forces, we notice the 1,500 is not going to show up because it's going down the X. But the 1,000 is going to be in this direction. And look, it's aligned with the Z, so you can even just use your ruler and see that that's a Z force. And then we have this 800, and you can notice that it's going in the negative Y direction. Now, taking a look at the dimensions on this, we'll notice that this one, once again, is passing through this point. This is the point where we're going to want to take the moments about. But this 800 right here, it's got a moment arm that's going to be 5 inches long right here. So this is to scale, actually. I believe, yes, yeah. And so this is the 3, and this is the 5 that's right there, right? So let's label that 5 inches onto this, right? And so we could do the sum of the moments. Well, I didn't draw my reaction forces. Let me draw my reaction forces. We have a reaction force that's coming up. That's going to be my RY, right? And then we're going to have an RZ. And I don't really, in this level of problem, need to find out. I know that RZ is going to be equal to 1,000. Only forces in the Z direction. I know already that RY is going to be 800. Actually, I was able to find it from over here, so I would have already found it. But we do the summation of moments that are happening about the X-axis here, right? So that's the twisting one. And that has a special name, right? That's actually the torque, right? Because that's the one that wants to twist this thing about a long axis that's causing a twisting action. So we call that one torque. And we're going to remember that we always wanted to keep track of the sign convention. So I always put that right here next to this sum of the moments, sigma, right here. This tells us that counterclockwise is positive. And we know that this is going to cause a counterclockwise. So it's actually the reaction is going to be clockwise. And we want to draw that in the appropriate way. And I'm going to draw that like right around there. Trying to get the arrowheads in the way of each other. And I'm just going to call this T in this case, right, for torque. And so if I'm going to write out this thing, I'm going to go negative T plus 800 times 5 equals 0, right? And so we would say that torque is going to be equal to 4,000 inch pounds. And maybe we want to label this, right? So you got to be careful when you label the direction arrows of things. You need to make it associated with a diagram, right? Because it won't make much sense. But this one is clockwise, or I guess maybe you could just go ahead and you always use the whatever is the global coordinate system, so it's probably usually pretty standard right here. It just depends on the orientation of the thing, right? Sometimes it doesn't make a lot of sense to label stuff always using the exact same coordinate system, but most of the time. All right, so that was a clockwise one. We're reminding ourselves this one is a counterclockwise. So maybe I'll put that on there. All right, so here is why. All right, so we just did some simple ones, and this is why people mess this up. Because they do too many simple problems and they run across a non-simple problem. We don't always know the direction of the moment. Now, in this case, easy. This case, easy. We could tell just by observation. But here, when we're taking the creepy eye and we're coming down from the top, right? So, and I can decide which one's going to go downwards. I think I decided that Z was downwards, so I guess the eyelashes are kind of coming over here. So he's kind of looking down that way onto the thing because I already drew it, right? But yeah, it makes sense to have Z coming down here. Okay, so let's draw what the forces are that are on this thing, right? For one thing, 800 is coming into the page, right? So we're not going to be able to see that one. The X is a good place to start, right? So X is that 1500, right? It's coming right here. And so X is in this direction. So we're going to have our 1500. It's going to be right there. 1,500 pounds. And then that 1,000 pounds, looking down on this, is in the Z direction. And so it's going to go in the positive Z direction, right? So that's another clue that we can use if we haven't figured out what direction forces are going to go when we're trying to draw three views of the thing. Now, some of the dimensions we might want to look at. We know that this right here is 5 inches. So we got the 5 inches. And this direction right here, let me go ahead and label it down over here. It's going to be 3 inches, right? And I went ahead and I ignored how thick this thing is right there. We can see that it has some thickness. We just decided that the dimensions were labeling it from the center of the thing, so we're not gonna be really fussy about those. All right. So the reactions, forces that are being placed on here, all right, this is going to be Rx, which we would have found from over here previously. And then we also have RZ, which we know has to go that opposite direction from here. And there could be multiple forces onto this piece. So, we can't always just we might actually need to write out the sum of the forces to be able to find what the ultimate reaction is going to be. But right here, we just know because it's simple that they're right here. Now we need to take the sum of the moments. And, we need to figure out what the direction of the reaction is going to be. Here's one where we don't know what the answer is going to be just from observation, because this force is trying to go clockwise, right? So it's a force that's coming this way right here. It's going to be acting through that 3 inches, right? And it's going to try to turn the thing that way right here. So a reaction of it needs to go, this is going to try to go clockwise because of that. So the reaction would need to be counterclockwise. But that 1500 is going counterclockwise. So a reaction due to that is going to be clockwise. So this is really sort of like superposition that's actually taking place here. We have two different things happening on. We're going to put them both, we're going to add them up, and we're going to see what the reactions are going to be. So a good thing to do when you don't know is to go as the default, right? As being counterclockwise, right? When you don't know the answer. So we take that, and I'm going to call it MR, and that's going to be about the y-axis, right? Remember, we're looking down upon this thing up here, and that's what we're seeing, right? So I'm gonna give down here where I have some more space and say the sum of the moments about the y-axis is equal to 0, right? Remember that this is the actual moment that's inside this piece, right? So And this is just saying generally all the moments that are about y. So I'll write out that first one, MRY, and then I'll apply this one first. And that's going to be clockwise, I said. So it's minus 1,000 times 3. And then this one's going counterclockwise, right? It's going to go that way right there. So it's going to be plus 1,500. And then the distance that's perpendicular to its sense is 5. And we get equals to 0, right? So what we will find from this, if we said, we'll see that this is going to be, what is 5 times 15? Is that 7,500? I think so. And then this is 3,000, right? So this is going to be positive 7,500. And this is going to be negative 3,000. So it's going to be positive 4,500, but it needs to go on the other side of the 0. So MRY is equal to negative 4,500 inch-pounds. But that means we chose this one incorrectly, right? So it's actually equal to 4,500 inch-pounds clockwise, even though it's drawn here as counterclockwise. Well, you're going to need to remember that. All right, so a last step that I like to do, and I really encourage you to do it, is to now, instead of drawing the forces onto this piece, move them over to this piece. Because this is usually where I think we want to analyze the stresses. And we will see in class 2, I'll use the same example, and we'll pick this apart and think about the stresses that are caused by the statics. But this is a class dedicated to just learning, refreshing on statics. So these are reactions. These are equivalent forces and moments. Reactions on the free body diagram, reactions to the loads. Here, instead, we want to transfer the forces that right here to this new location, because here's where we want to know the stresses. Here's where we want to know what's happening. So we're going to break this apart and transfer those loads. And when you do a cross product, that's what you're doing. You're transferring the loads from over here to this location that you care about, the section of interest. And when you do that, you get signs that are going to be the opposite from the reactions, because the reactions are over here. So we have equal and opposite reactions right here within this section. Some of them are taking place on this side, some of them are taking over here. But I believe that these over onto this piece, after you've done getting this, moving them over to here, helps you to pick those stresses apart and actually visualize those stresses. So as confusing as it might be to have done all this work and then just transfer them over here, I think it's worth the hassle. So what we want to do is, first off, let's just put all the loads. We see the loads just transfer over, right? Here where the directions of the loads, well, they're the same when we move them over to this spot. So we just have down, and we have over, and we have here, right? And so this one is 1,500 pounds, and this is 800 pounds, and this is 1,000 pounds. Okay? And now for our motions that are happening on here, well, let's take it one at a time. Here's in the x direction. We found this one, the solution was clockwise. Well, this one is counterclockwise because it's equal and opposite. And that one just makes sense, right? Because we have a force that's coming down here on our door handle. That's the one that's trying to turn the door handle. It's going to turn this thing and make it rotate. So it's going that way, going counterclockwise. It just makes sense, right? We could just, from observation, we could pick that one up. How about the z-axis? Right? Okay, so the z-axis, once again, is that 800 pounds. He's the one that's trying to do it. And he's trying to push downwards and move around here. So that one is obviously causing a clockwise motion right here, right? And I don't have a really good spot to put this in here. I might move my 1,000 out of the way, right? So that's always like a little a little graphic artist thing that you got to try to do. Try to make sure we keep that these things so we could label them, we could understand them. And so that one is, I didn't write what this one was going to be. I should have written what this was, the 4,000 inch-pounds. And this one it is the 2,400, right? So I'm just going to put it as the number 2,400 inch-pounds. And this last one, we've got to be careful here. This one says that we're going clockwise, remember now. So we have to use our right hand rule this way, right? We use our fingers to wrap around the direction and our thumb points there. So this one is saying clockwise, which is, so if this is clockwise, this has to be counterclockwise, right? Remember that this is clockwise, right? That's trying to, so the reaction is coming this way, right here, right? So here, it's actually making a motion that's counterclockwise, right? Let me see if I said this wrong. Well, I think I said that wrong right here, right? So this one is trying to go clockwise, right? That's the reaction of this that's trying to stop this motion. So if this one's clockwise, this one is counterclockwise. So it's coming that way, right there. Because remember, default is positive. So our right hand, if we're wrapping around, if our finger's pointing up in the positive y direction, then our reaction is coming this way. So this is the direction that it motions. And so that's going to be the 4,500 inch-pounds. And the really reason why so it's right there, 4,500 is coming around because this guy right here is counterclockwise, right? Our fingers are coming around and we're pointing our thumb into that axis. And why do we care? Why do we care about that? Because we need to decide, and so I'm jumping ahead to class 2, but you took mechanics and materials already, so this is a refresher in that. You need to decide what's happening at B. Is B, when we put a stress element in there, and we will do that in the next class, and I'll put these little stress elements inside. See if I can get my little eraser bits to go inside this right here. We need to decide, is B in compression or tension? So we need to find out whether this thing is being pulled apart right here, which is what's going to happen if you have a clockwise motion about this, right? So, counterclockwise. If counterclockwise, if it's spinning this way right here, that tends to pull this apart. If it's going clockwise, it tends to push it together because it's rotating about that axis. And it's much easier to think about the stump than it is to think about the free body diagram. So that's why we want to push it onto this little piece in the section of interest. So I will show, I think I have a demonstration where I do a cross product. And you'll see when we do a cross product on a problem that looks like this right here, we're actually going to get this answer. These are the directions that we will get for our answer when we do a cross product. And they are what we'll call the equivalent moments, right? Equivalent moments because we moved the location of the forces from here to over here. All right, so that was a longer video than I meant, but I wanted to go into a lot of detail with it. So let's see, how did we do? It was a 28-minute video. But some people really need this amount of looking at the thing to really pick it apart. So I'm going to refer back to this video often for you if you're struggling with the thing. And we can walk through it together during office hours as well. So I really want you to own this. So thank you, and we'll make another video. Boy, it took 28 minutes to do that. It's a long time. All right. See you soon.